And I think I relate to the point that you mentioned that steam is actually just an intermediate utility. So even if we are talking about it from a perspective of carbon footprint, as an example, you can have renewables. So this is a typical example I usually interact with, is that you can have renewables play a bigger role in your energy mix. But for process heating applications, you always require steam as an intermediary because there are many advantages associated. So anything from textiles to paper, rubber, you're looking at cement, any industry that requires some heating in the background will always require steam. You may find different means of generating it, but at the end of the day, that will still play the intermediate role. So to ask, I want to build up on that conversation itself, which is that why is steam so popular? Why is it so relevant even in modern day? Okay, so again, coming back to the obsolete point, power has found an alternative, but the process heating part still doesn't have one. So what makes steam so attractive in that context?
So if you look at it again as an example, have people tried to look at alternative energy inputs as a utility? Yes, they have. There are many processes who have tried to move away from steam to, let's say, thermic fluid. So I'll give you another example to just back up what happened in one of the plants. So there was a dairy plant. We all know that milk, which is what we consume, goes through a process called as pasteurization. Pasteurization takes place at a temperature of 72 degrees Celsius. They call it as, a typical word uses high temperature, short time, which means 72 degrees Celsius, the milk is held for 15 seconds. Now, what am I trying to say? I'm trying to say that two things. One, you have to hold the milk for 15 seconds at a particular temperature to get the pasteurization process completed. So when the dairy experimented with thermic fluid, I'll come to why they experimented a bit later, but let me first talk about, the relevance of steam as a utility. They tried to really look at it in terms of what they could do to really get it with thermic fluid. They had serious problems. Thermic fluid systems are not easy systems to handle. If you have a leakage, you are playing with hot temperature thermic fluid, which is just going to spill over. There is a slight amount of hesitation and inertia to thermic fluid systems because they are slightly toxic in nature. There is a slight amount of aroma or odor which is there. Look at steam.
Right.
Clean, that's what I said. Odorless.
Yeah.
Colorless as long as it is dry saturated. So you are really trying to look at what? On one hand, a very critical thing like milk pasteurization, and you are looking at steam as a utility, you will understand the importance that steam plays a very crucial role because it has a capability to look at saturation temperature and corresponding pressures which are decided by thermodynamics. Of course, it is physics behind all this, which we have to be mindful about. But that's something which is so pipeable. It's something which you can maintain. It's easy to really keep the controls. Here, I would say that there are two aspects to it. One is the pressure at which you are really carrying the steam up to the utilization point, and then the precise process temperature control basis the flow variation in the steam consumption. So that's something which is very easy with a steam network. Most other utilities, if you take thermic fluid systems, hot water systems, they have a huge inertia to giving away energy. Now that inertia would mean that your time temperature profiles are all one for a toss. Now where is this 15 seconds coming into picture if you have an inertia to really exit energy into the process which you are trying to manage? So those things which are nuances. Now today we are going to UHT, which is ultra high temperature for pasteurization. The temperature requirements are 135 degrees Celsius. Time is again a very crucial factor there. Right. So how do you get into UHT as a process if you do not use steam as the utility media? So that's, I think, making it more and more relevant that as the science has progressed, steam has stood out as the first choice because of three specific things, I think. One, it does not need any energy to pump itself from one end to another end.
Yeah.
We are finally looking at carbon footprint. Right? You do not want to run pumps to look at pumping a utility from one point to another. The second thing, it's one of the uniqueness of steam as a vapor media is it's compressible.
Correct.
We should never forget that you want to carry steam from one end of the plant to the other end of the plant where you have the utilization. If that's the layouting, and there are many reasons why the layouting couldn't be compromised in a different way or restructured in a different way. So if we have that choice to really go for it, then the compressibility gets you the clarity that you can have a smaller diameter pipeline just by pushing up the pressure or carrying the same mass of steam.
Right.
And the third and the most significant factor is its capability to dissipate its energy quickly to the process which it is trying to get up with.
Yeah.
And that dissipation of energy, which is latent heat, I don't want to get into too much of technicality here, but that latent heat content in steam is something which makes steam the most meaningful media for heat exchange. It has the highest heat transfer coefficient.
Right.
That makes it the cheapest utility.
Right.
And I didn't want to come to cheap as the first starting point because as engineers, we will have to somehow be mindful that whatever is cheap has to be ideally suited as well.
Yeah.
And that's where I was trying to reframe myself from using the word cheap as the first choice. And I was trying to look at the energy and the capability to look at production processes and process efficiencies primarily to far outweigh even the cost of steam as a utility as compared to other utilities.
Yeah, that's actually right. I mean, a lot of things that you have mentioned make steam a very flexible media, in terms of its versatility in almost every process heating application. Whether it is milk, the example that you gave, or whether it is pharmaceuticals or the sterilization process. So steam can play its role in any context because of its non-toxic, self-propagating nature. But I definitely want to touch on the point that it has a huge reserve of energy, which it is very easily or willingly able to give. So it's unlikely that irrespective of what your process requirements are, steam is never going to stop giving. Giving that's the beauty of it essentially. Any other system you may have to end up scaling up or down, but as long as you have a consistent supply of steam, the process is unlikely to starve. So that's a very attractive option in that case.